The asteroid redirect mission at the end of this video shows that they will bring a segment back to a sample back to Earth. That's something that I believe, I'm sure many people believe, that is dangerous. It could be contaminated with something that would flourish on Earth and would, of course, be dangerous to all life on Earth. So that's something I think should not be done. Bringing something from an asteroid back to Earth, handled by astronauts and brought back to Earth as a sample.
Evidence that impacts occur. We know that they've happened all over our solar system, all over our planet. So this is why we have started surveying for asteroids. We know that actually trying to do surveys that are capable of finding objects well in advance of when any potential impacts occur gives us the widest range of possible things that we can do about it. Civil defense basically means evacuate people, move them out of the way. And this is what you would do if you have very short warning times. So the kinetic impactor is probably the most familiar, and the Deep Impact mission vividly demonstrated that it is possible to mount such a campaign. Then if you have more time, the gravity tractor idea basically requires a lot of time, but it offers potentially more carefully controlled ability to move an object. So being ready in my book means you want to have demonstrations that you've already done. It's also very, very important to have continued support for radar. Radar observations are incredibly important for doing a wide range of things that we need. They can offer the best possible tracking of an object short of actually being there with a spacecraft. Being prepared for the future involves having instruments that have both large apertures but also wide field cameras to be able to capture objects and track them. And it would be really nice to have spectroscopy and colors to be able to get some idea of taxonomy and composition. And international cooperation is essential for this, just because of the nature of the problem. I would say that NASA has a great start on this. Through the formation of the Planetary Defense Coordination Office, we want to have the connections already made, have them well exercised, and understand who to talk to, regardless of where an impact is predicted to actually land on the Earth.
The Sky Survey and other survey programs are really sort of the start of the whole planetary protection ecosystem. It starts with discovery, goes on to follow-up and characterization, impact risk analysis, mitigation studies, but you can't follow up and you can't characterize and you can't calculate the impact risk of something you don't discover. In order to find a near-Earth asteroid, we take 4 images of a patch of sky separated by about 5 minutes.
And we take those 4 images and we blink them really fast, and it creates this little animation so we can see that the stars in the background are static, as they should be, and if there's anything that's moving, it'll pop out.
And our software compares those images and identifies things that are not moving, which are stars, and removes those, identifies things that are transient from frame to frame, and tries to link those up.
We've probably seen about 1 million asteroids in the last 7 years that the Pan-STARRS has been operating. It's like picking a needle out of a haystack. We're looking for distinctive motion, and when we see distinctive motion in asteroids, we report them to the Minor Planet Center. The Minor Planet Center is the sort of world clearinghouse for near-Earth asteroids.
The Center for NEO Studies takes the observations from the Minor Planet Center and computes the high-precision orbits that we use to make predictions. CNEOS is also kind of an early warning system for newly discovered asteroids. We take the early data and we compute whether or not that asteroid could hit the Earth. If there's a chance, we'll send out an early warning and alert for follow-up observations so that we can get more data, and then we would know perhaps whether it can hit the Earth or not.
Asteroid impacts are a fact of life. The Earth has been impacted by asteroids continually through its history.
We saw in 2013 in Russia a fairly small, by the standards of what we're finding, asteroid did hit the Earth. I feel a little bit like a guardian of the planet and doing my bit to try to protect people. It is a long-term process. It's going to take many, many years to find all of the dangerous asteroids.
The goal is to find near-Earth asteroids before they find us.
Dinosaurs were fearsome creatures. Some had thick scales, sharp teeth, and in many cases, lightning-fast reflexes. One thing they didn't have, a planetary defense office. When an asteroid targeted Earth 65 million years ago, it took those masters of Earth by complete surprise. While we know of no large object that is on a collision course with Earth in the next 100 years, descendants of survivors from that catastrophic impact are determined not to make the same mistake. In 2016, human astronomers now routinely scan the heavens for signs of potentially hazardous objects. When one is discovered, alerts are issued to observers around the world, so space rocks cannot easily disappear into the blackness of space. NASA-funded survey projects have found 98% of the known catalog of almost 15,000 near-Earth objects. Asteroids and comets whose orbits periodically bring them within 30 million miles of Earth's orbit. The list is growing at a rate of about 1,500 per year. Meanwhile, researchers are giving serious thought to an even bigger problem. What would we do if a dangerous asteroid is discovered? How will we know if and when it will impact? Is it possible to deflect or destroy it before it reaches Earth? All of this work, from discovery to tracking to potential mitigation, is being done by a sprawling network of government agencies, private and public universities, and both amateur and professional astronomers. Helping them work together is the job of NASA's Planetary Defense Coordination Office. Lindley Johnson, Planetary Defense Officer at NASA headquarters in Washington, D.C., says, "Planetary defense is a team sport." This office was established at NASA headquarters to coordinate the players in planetary defense-related activities across NASA, other U.S. government agencies, and with international efforts and projects to detect any asteroid impact hazard and plan the appropriate response. A recent real-world example illustrates how all this works. Paul Chodas, manager for NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory, describes what happened. The object was first detected by the NASA-funded Catalina Sky Survey near Tucson, Arizona on October 3, 2015, and tagged as detection WT1190F. Within a couple of days, astronomers suspected it was probably an artificial object. It was faint and small, with its motion visibly altered by the gentle pressure of sunlight, a bit like a solar sail or perhaps a hollow rocket body. As tracking data accumulated from multiple observers, astronomers realized that they would get a closer look. This would be a real-world case to exercise the team's skills. WT1190F was predicted to hit Earth on Friday, November 13, 2015. Orbit calculations by JPL analysts pinpointed the impact time and site. WT1190F would burn into the atmosphere off the coast of Sri Lanka. For years, Peter Jeniskins of the SETI Institute, working with NASA's Ames Research Center, has been leading teams researching entry dynamics on airborne campaigns to observe objects ripping through Earth's atmosphere. In 2006, for instance, they recorded the return of NASA's Stardust Sample Return Capsule with its cargo of cometary dust. They've also observed a number of defunct spacecraft re-entries and a few natural meteor events. Supported in part by the United Arab Emirates Space Agency and the International Astronomy Center, Jeniskins assembled a group of experts to witness the re-entry of WT1190F. They flew to the Indian Ocean on a G450 aircraft armed with cameras and spectrometers. Exactly at the time and place predicted by NASA's Near-Earth Object Observations Program, WT1190F produced a magnificent fireball in broad daylight. Jeniskins says the spectra of one large fragment contained bands of titanium oxide and a line of hydrogen, so the object could have been a titanium-walled vessel containing residual fuel. Chotis, who had been attempting to reconstruct WT1190F's past orbital motion, says, "My educated guess is that it was Lunar Prospector's translunar injection module, which had a titanium case, although we may never know for sure. One thing is certain. Astronomers supported by NASA found it, tracked it, and predicted where it would hit with pinpoint accuracy. These are exacting skills that will come in handy the next time an actual asteroid comes to visit." For more about asteroids and NASA's planetary defense capabilities, go to www.nasa.gov/planetary defense. For more on objects both near and far from Earth,
Kindly support by contributing to my Patreon account. You'll find it in the description box below. Thank you.